15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hello, my name is Ed Espinoza, and I first want to thank the organizers GTTN for allowing me to participate, although via these digital forms on this conference. I am really sad I cannot be there present and meet you all, but at least I was given an opportunity to share with you some of the work that we have been doing with mass spectrometer in the field of wood identification. In our lab, we do two things when we receive some evidence of wood. The very first step of an analysis involves using macro anatomical analysis, and to do that we use the criteria and the different features that are identified in CITES wood ID and inside wood. And once the genera is determined, then we proceed to a second step and we use mass spectrometry to do specific species identifications. So the rest of this talk is really a little bit about what is DART TOFMS and how does it apply to wood ID. DART stands for Direct Analysis in Real Time, and in this picture it is this blue components of this instrument. DART is a atmospheric pressure ionization, unlike GC or LCMS, in which samples needed to be prepared either into the gas phase or in the liquid phase. Here a sample is analyzed directly, and in this picture you can see a close-up in which a piece of wood is placed in the interface between the DART and between the mass spectrometer. The amount of sample needed to do this is very small, and on this picture you can see the slivers that we are typically using for doing analysis. And the fact that it is so small has been very useful because many times when we go to silaria, there is little opposition of us sampling a sliver of wood as compared to a chunk of wood that sometimes is needed for other techniques. Here I'm going to show you a video of the typical process that we use when we're collecting a sample. This involves both all of the steps of extraction, cleaning, purification, and analysis. Okay. And that is a process. And it is surprising that we get so much data out of a spectrum of only 8 seconds or less, and I will show you some of that. This is a typical spectrum of a piece of wood. This happens to be a sample of Swettinia mahogany. But what you see are a bunch of peaks. And these peaks are usually very useful for determining the presence or absence of a specific molecule. And if that molecule is diagnostic or species specific, one can make an inferences of species. So in this slide we have another spectrum of Delbergia negra, and you can see the different peaks associated with that sample. And each one of those peaks of course has a name, and that name is associated not with a random name but really with a three-dimensional molecular structure that has a purpose in the timber. We now know that these chemicals are genetically inherited, and the purpose may be either anti-pest control or some other growth hormone purpose. And it's not surprising that there are unique chemicals to the two different trees, because Tony Swain in 1963 proposed that you could use chemical analysis to make some inferences of taxonomy. This work was extended in 1987 by William Hillis from Australia, in which he showed that a greater amount of chemicals he identified, both looking at exudates and other types of material from timber. What is news and what we're offering is that when you have a population of samples, meaning different individuals from the same species, then you have a robust collection of data. And once you have a robust collection of data, you can characterize species that do not have unique diagnostic markers, or you can characterize populations. And in this slide we're showing that you can do non-supervised inferences using something like heat map, which we'll talk about in a minute, or you can use hierarchical cluster analysis. Additionally, this kind of data presents itself or lends itself to do multivariate analysis. Many people ask, so where are these chemicals? And we have done some experiments to show that in this cross-section we show these vessels, and these vessels are filled with compounds. And in this case we can see a creamy looking compound, a dark looking compound, a gray looking compound, and each one of these vessels is where the phytochemicals that we're identifying are found. So I'd like to give you an example looking at the Araucariaceae family, a species that occurs usually in southern latitudes but also in parts of North America. But before I do that, I want to briefly talk about what a heat map is. In this slide, in the top part, we can see a typical spectrum. This happens to be the spectrum of Delbridgia nigra again. And each one of these peaks corresponds to a compound. A heat map demonstrates populations in which the horizontal axis is the mass between 70 and 806 atomic mass units, and each row is a different individual of the same species. So here we have about 20 samples of Delbridgia spruciana and about the same amount of Delbridgia nigra. Each column represents a particular compound. And so if the compound is found at a high intensity, then the compound is seen here at a darker scale. If the compound is found at a low intensity, then you can see that at a lower coloration scale. So in this particular case and in this heat map, you can see that Delbridgia nigra, with the presence of caveunine, can be distinguished immediately from Delbridgia spruciana by the presence of compounds or the absence of compounds found in one or the other species. And for those of you who have struggled with the anatomy of these two species, know that determining species from Delbridgia nigra and Delbridgia spruciana using traditional anatomical features is very difficult. For the work we did with the Araucaria group involved these species, and again, this is another group in which the anatomy is such that it is very difficult to distinguish, in this case, Araucaria araucana, CITES Appendix 1, from Araucaria angustifolia, not listed, both of them coming from Argentina. Sometimes angustifolia comes from Brazil. In one case, there's a healthy trade. In the other case, it's completely banned. So, to start with, we'll look at the heat map. At the bottom end of the heat map, below the red bar, are the heat map results for Araucaria araucana. And immediately upon looking at this, you can determine that it is missing or has a lower intensity of compounds than you see on the closely related species, Araucaria angustifolia. And in some cases, you have, like here, a compound that is present pretty predominantly but absent completely in the bottom. And so it is immediately distinguishable from the other taxa in this group. A little bit more difficult to distinguish perhaps from Araucaria heterophylla, a species from North America. And then very different, the top two segments of the Agathis group found in Australia and New Zealand. You can see also some differences between Agathis and Willemia, the fabled extinct fossil species from Australia. So if in this case we do a supervised kernel discriminant analysis, you can see that we have clustering very uniquely of the different groups that we're looking at, and the group that is closest together is the Agathis australis and the Willemia nobilis, and the other three groups are completely separated. Validation of this model is using a technique called leave one out cross-validation, and in this case we have a cross-validation of 87%. This validation technique takes each sample from the model set, excludes it, and poses the question, who does this spectra belong to, and then places it back in, and it goes sequentially until all the samples from the model are used. And 87% basically means that 13% of the time it got the incorrect answer and all the rest of the time it got the correct answer. In looking at the data carefully, I realized that the 13% error was involved in these two groups, Willemia nobilis and Agathis australis. And the reason is probably because we don't have a robust sample size of nobilis samples. When we move to the next technique, which is hierarchical cluster analysis, we find that we get very discrete separation. The species from New Zealand are separated immediately from the species from the Americas. And within the species of the Americas, we have Angustifolia as a specific group. We have Heterophylla as a specific group, and then Araucana. And within the Araucana group, we have two samples from Angustifolia that seem to be misplaced within this cluster. In looking at the source of these samples that came from a colleague from the Forest Product Lab in Wisconsin, it was found that these two samples were from commercial vendor sources and their origins are really suspect. And so the conclusion that was arrived after examination of the paperwork associated with it is that these samples probably are Araucana and not Angustifolia as the paperwork had originally described. So, let's look at the big picture. Recently there was an estimate that there's about 40,000 tropical tree species in the world. If one considers areas beyond the tropics, people have said there's roughly 100,000 described species. Inside wood currently has roughly 7,159 species described. 18% of those are tropical species. And some of these species are in fact from fossil descriptions of fossils. What do we have from a DART TOFMS chemotypes? Well, we only have 147 species to date, and that is a very modest 0.4% of all tropical species known. But if we look at the data slightly different, and let me explain this graph. This is the graph of all of the groups, the taxonomic groups, protected by CITES at this point. Groups in green are taxa to which we have good representative samples. Groups in orange are groups that we have been promised samples or we're about to receive samples. Groups in white are species to which we don't have a single specimen, and in some cases they've been impossible to obtain. When I look at the groups of samples that we have and compare it to the groups of CITES that CITES lists, we cover roughly 51% of CITES species. A comment about this table: when I say Delbergia spa, I'm roughly talking about 60 species. Only one of those species is CITES Appendix 1, Delbergia negra, all the rest are CITES Appendix 2, and this number varies between 48 and 60 depending on the taxonomic source that you use. And so this is just an overall average of CITES listed species and our in-house capability to do species identification at this moment in time. Here's a summary of cases that our lab has dealt with since roughly 2014. We have had about 60 law enforcement cases, about 390 items, and it includes various types of materials such as timbers or guitar kits, which most of the time are veneers, violin bows, incense and oils in which there is no morphological characters left. We've looked at some wood from shipwrecks and antique furniture. And on the right side column you can see there's an example of species that we have characterized using the techniques that I have just described, with the exception of the cases in which there is no morphological characters present. Another question that's been posed to us is, what is the persistence of these chemicals in the hardwoods or of the chemotypes? And here's an example of 5 different experiments that we've done. 6. We've had examples of sunken torpedo boats that were Spatinia mahogany, had been sunk for over 50 years. We have examples of timber from Madagascar that was carbon dating 220 years. We have had Aquilaria samples from the Imperial Vault of Heaven in China, 260 years. We've had samples of a sunken Spanish galleon from Portugal. This wood was underwater for 260 years roughly, and it turned out to be Quercus faginea. And lastly, we have Cory wood, admittedly an oddball in this group, but over 50,000 years because of its preservation. So the point of this slide is to say that these chemotypes are in fact preserved, and there should be little concern if a chemotype is preserved over time. Other applications of DART TOF so far has been determining wild versus plantation. We've done geographic source assignment. Some species are very specific to a particular geographic source. We have done some inferences of rainfall looking at specific molecules. And we have done validation of Sileria specimens. And in one case we were able to identify some inferences of hybridization from two different species of Swettinia that occurred jointly in some of the Caribbean islands. Overall conclusions? Well, 147 species analyzed so far, over 3,000 specimens. Of these, roughly 87% have species-specific chemotypes that can be used for diagnosing a species. Wood anatomy and metabolome profiles together are very useful for making species identification of CITES heartwood. We now know that environmental or temporal effects does not significantly alter the chemotypes, and this data was not necessarily shown on this slide. And lastly, I wanted to highlight that there's been over a dozen publications of this work. At one point this was kind of novel, but now it's been used quite a bit, and so if any of you have an interest in getting any of these papers, I'd be glad to share them with you. You can send me an email at the following address. Thank you very much for your time. I appreciate the opportunity to share with you the work we've been doing.